This is the architecture of industrial data. Visualize every data system in a facility as an isolated island. The SCADA system, the MES, the ERP, and the maintenance platform each exist in their own separate silo. To share data, engineers build custom bridges. But when one system updates, the bridge breaks. This requires more custom code and more bridges. The complexity accelerates until a single point of failure becomes impossible to isolate. This brittle network of custom connections is the current reality for 90% of manufacturers attempting digital transformation. The Unified Namespace offers an alternative architecture designed to centralize these data flows, moving away from the reliance on individual point-to-point bridges. In enterprise architecture, this specific point-to-point problem is known as the integration hairball. The issue is driven by a geometric scaling rule. Every time a new system is added, it requires a unique connection to every existing system that needs its data. The math proves why this is unscalable. 5 systems require 10 potential integrations. 10 systems require 45. By the time a facility reaches 20 systems, it is managing 190 separate custom connections. Each connection is a liability. They rely on varied data formats, different latency characteristics, and custom code that is often poorly documented. Most IT managers at mid-size plants maintain a significantly higher number of these custom integrations than their leadership realizes. Legacy SCADA systems were designed for isolated process control. They lack the structural foundation to serve as a data backbone for a modern enterprise with dozens of consuming systems. The modern unified namespace concept was formalized by Walker Reynolds, an industrial automation architect whose work on MQTT-based architecture has shaped deployments globally. His framework combines publish-subscribe messaging theory, ISA 95 organizational standards, and the practical observation that legacy SCADA-era integration patterns cannot scale. This architecture is the foundation for the Syntag platform and the starting point for every IIoT deployment in our portfolio. SCADA, Supervisory Control and Data Acquisition, was a breakthrough for the late 20th century, providing centralized visibility over remote physical processes like power grids and pipelines. The architecture is hierarchical. Remote terminal units in the field communicate with a master control station using protocols like Modbus or DNP3. This remains essential for process control, but it contains 4 structural limitations that prevent it from supporting modern IIoT needs. First, proprietary ecosystems. Data is often trapped inside vendor-specific historian formats in HMI screens. Second, pooling architecture. SCADA systems retrieve data on fixed cycles, which means the data rate is limited by a preset schedule. Third, the forced integration hairball. When an ERP needs data from the plant floor, it usually requires a new, custom point-to-point connection to the SCADA database. Finally, OT and IT separation. SCADA was designed for isolated networks, making it difficult for operational data to reach analytics platforms and AI systems. The unified namespace shifts the architecture. Instead of systems integrating with each other, every system publishes its data to and subscribes from a single namespace. This namespace is managed by an MQTT broker, which sits at the center of a hub-and-spoke network. Every data source, from sensors to PLCs, publishes to a specific topic in the namespace. Every consumer, like an ERP or a dashboard, simply subscribes to the topics it needs. The namespace is organized using a hierarchical structure that mirrors the enterprise, moving from the site level down to individual measurements. This uniquely identifies every reading. In a multi-site setup, a single temperature sensor is located at a specific path: Acme Corp, Cebu Plat, packaging area, line 3, filler B, temperature. Adding a new analytics system or a new factory is simple. New systems subscribe to existing topics or add new branches to the tree without requiring changes to any other part of the network. This creates a single version of truth across the enterprise, with no synchronization lag between systems. A traditional historian stores time series data for historical queries, allowing users to look back at what happened previously. While a historian archives the past, the unified namespace operates as a live data bus, streaming real-time operational data that any system can tap into at any moment. In this architecture, time series databases and analytics platforms act as subscribers, pulling data from the broker for processing and storage. This also differs from a data lake. Data lakes ingest volumes periodically for batch analysis, whereas the Unified Namespace provides millisecond latency streams for real-time operational decisions. These systems are complementary, serving different timescales and different operational use cases. Refactoring an MQTT topic structure later is expensive because every subscriber must be updated. This makes the initial design critical. For manufacturing, the ISA 95 hierarchy provides the standardized reference model for organizing these topics. Rule 1. Use your enterprise hierarchy, not your product lines. Plants and lines are stable, whereas the products made on them change frequently. Rule 2. The final leaf in the topic must be a human-readable measurement, like pressure or temperature, rather than a raw register address. Rule 3. Be consistent. If every plant uses the same naming convention, wildcard subscriptions can reliably capture data from across the entire company. Rule 4. Keep units out of the topic path. Put the units inside the message payload, so the topic remains a clean routing path. Rule 5. Version your namespace. This allows legacy subscribers to continue working on an old structure, while new systems transition to an updated version. 1 week spent on architectural discipline at the start prevents months of painful refactoring later. Implementing a unified namespace is an incremental process that can run alongside existing SCADA infrastructure rather than replacing it immediately. Phase 1. Identify the 3 to 5 machine data streams that would provide the most immediate value if they were available in real time. Phase 2. Install an MQTT broker on your operational network to serve as the foundation of the namespace. Phase 3. Use industrial gateways to connect your first data sources to the broker using your new topic structure. Phase 4. Connect your first consumer, such as a dashboard or visualization tool, to make the data visible to the team. Phase 5. Connect business systems, like your ERP, as new subscribers to the existing broker. Over time, the unified namespace becomes the enterprise data backbone, while SCADA remains focused on machine control. We began with 12 islands and 38 custom bridges, all prone to failure. The unified namespace functions like a harbor, a single place where every system docks and exchanges information without the need for custom connectors. Find the single most frustrating data integration in your current system. Replace that one connection with an MQTT-based pilot and observe the results. Next week, we will examine the physical layer, comparing the trade-offs of LTE, Wi-Fi, and wired LAN for industrial connectivity. Subscribe to stay updated. The architecture is taking shape.